Ever wondered what actually happens when you double-click an icon on your screen? How do those lines of code, which are really just simple text, magically transform into a full-blown application? Well, I promise you, it's not magic. Today, we're going to follow the incredible journey of a C program, from just an idea in a programmer's head, all the way to a running program. Yeah, this is the big question, right? On one hand, you have source code, basically a text file filled with instructions, and on the other, you have a final working program. So what happens in between? It's this brilliant, logical process that's pretty much the foundation of how our entire digital world functions. You know, the best way to think about it is like this. Your C code is an architect's blueprint. It's got all the details, all the plans, but you can't live in a blueprint, right? You need a whole construction crew to turn that plan into an actual building. And that building, well, that's our application. This journey involves a few really critical steps. So, the first member of our construction crew is what I like to call the master translator. Its official name is the compiler, and its whole job is to take that blueprint and make sure the crew who will actually be building this thing can understand it. Okay, and this is absolutely crucial to understand. Computers don't actually speak C or Python or any of the languages we write in. They speak their own language, machine code, which is really just a bunch of ones and zeros. So the compiler's main job is to take our nice human-readable C code and translate it into those raw, low-level instructions that the machine can finally understand. The whole process is really a two-step dance. First, a good compiler acts like a proofreader. It scans the entire blueprint for any mistakes. And it is picky. A missing semicolon to you and me is a tiny typo. To a compiler, it's like a wall that doesn't connect to anything. Once it's sure the plan is solid, it translates everything into something we call object code. Now, this isn't the final program yet. Think of it more like a set of perfectly prefabricated walls and beams, all ready for assembly. Okay, so we've got our translated instructions. But modern programs, just like modern buildings, are almost never built completely from scratch. And that's where our general contractor comes into the picture, the linker. Its job is all about assembly. The linker is the master assembler. It takes that main set of instructions that the compiler translated, and then it starts looking around for all the other pieces it needs to create one complete functional structure. Think about it. An architect doesn't sit down and redesign a toilet or a light switch for every single house. They use standard, pre-built parts. Well, in programming, we do the same thing. We have libraries, which are just big collections of reusable code for common tasks like, say, printing things to the screen. The linker's job is to find those libraries and connect them to your main code, kind of like installing the plumbing and the electrical systems. The end result is a fully assembled building, ready and waiting to be placed on its foundation. So now we have our fully assembled building. It's complete, it's perfect, but it's still just sitting in the factory, on our hard drive. It's time for the final step, moving day. And this is handled by a super important component called the loader. Now, the loader isn't some separate app. It's a core part of your computer's operating system, Windows, macOS, Linux. The second you double-click that application icon, the loader just springs into action. It finds the program on your hard drive, picks it up, and places it right into the computer's active memory, or RAM. This is like moving the finished house onto its foundation and turning on the power. Only then can it actually run. So there you have it, the whole journey in 3 steps. First, the compiler translates the blueprint. Second, the linker assembles all the parts into a single building. And finally, the loader places that building into memory so you can actually use it. 3 distinct stages, 1 seamless result. So that whole journey is how it works for a compiled language like C. But is that the only way to do it? Not even close. Some languages you've probably heard of, like Python or JavaScript, take a totally different route. Instead of a master translator doing all the work up front, they use a live, on-the-fly translator called an interpreter. The difference in philosophy here is huge. A compiled C program is like a fully translated book. All the hard translation work is done beforehand, so when you're ready to read, it's incredibly fast. An interpreted program, on the other hand, is more like having a live translator whispering in your ear. It translates and runs your code line by line. You can start immediately, which is great for flexibility, but it can be a bit slower overall. It's just a classic trade-off between preparing everything up front or doing it as you go. So we follow this incredible journey from a single blueprint to a finished building. But that brings up a really fascinating question. How can one blueprint be used to build a structure that works on millions of totally different foundations, a Mac, a Windows PC, a Linux server?
That challenge, the challenge of portability, is what makes the relationship between a program and its operating system so important. And that, well, that's the next layer of complexity in making our digital world tick.